Welcome to the Deep Dive, where we unpack the research that matters, giving you the edge you need.
Today we're diving into something that honestly plagues a lot of advanced AI agents. Hitting the wall with context limits.
Yeah.
You give an agent a task, it starts exploring the web.
And boom. If the task is complex, needing lots of steps, that 32K or even bigger context window just isn't enough. The agent basically forgets what it learned earlier.
Exactly. It's a fundamental bottleneck for what they call long horizon search tasks. And that's where this new paper comes in.
Right, we're looking at ReSum, which stands for Reasoning and Summarization. It's a new approach from Tanguy Lab at Alibaba Group, aiming squarely at this context problem.
And the core idea is actually quite elegant. Instead of letting the interaction history grow indefinitely like the standard React framework does.
Which, just to remind everyone, appends every thought, action, observation.
Precisely. ReSum introduces periodic context summarization.
Yeah.
It allows the agent to sort of take a breath, consolidate what it knows, and keep going, potentially forever.
Okay, so let's do the quick takeaway first, the crucial bit for everyone short on time. What's the bottom line impact of ReSum?
Well, straight out of the box, without any fancy retraining, just implementing the ReSum logic, they saw an average performance bump of 4.5% absolute improvement over the standard React method.
That's already significant. Just changing the memory management gives a real boost.
But it gets better. They developed a specialized training algorithm called ResumeGRPO to teach the agent how to use these summaries effectively.
And the result?
The gains jumped up to 8.2% improvement over the baseline in some cases.
And what does that look like on a real-world benchmark? Because percentages are one thing, task completion is another.
That's the impressive part. Their final agent, WebResummer30B, hit 33.3% pass at 1 on a tough Chinese web browsing benchmark called BrowseCompD.
Wow, 33.3% pass at 1. How does that stack up?
It blows past other open source agents, many of which just can't handle these long tasks because of the context limits. It really shows that this kind of smart memory handling isn't just nice to have, it's, well, essential for complex problems.
Okay, that's the punchline. But let's dig into why this is necessary. Why does the standard React approach fail so often on these harder tasks?
The paper gives a great example query to illustrate this. It's quite convoluted.
Let me read it. A painter whose father died of heart disease had an elder sister and 5 children with his wife. Later, his marriage broke down and he had 3 more relationships. What is the name of the literary work based on this person?
See, it's tricky. You've got multiple entities, scattered facts, lots of uncertainty. You need to search for the painter, verify details about his family, his relationships.
Cross-reference maybe multiple sources. Yeah, that's not a quick search. You're going to need a lot of steps, a lot of tool calls.
Exactly. And the data they show backs this up. They looked at agents like WebSailor7B on an English benchmark, BrowseCompD.
And what did they find?
The tasks the agent actually solved. They were usually done in under 10 tool calls. Pretty quick.
But the failures?
Often took 20 or more tool calls. And you can see the token count just skyrocketed. It confirms the suspicion. The agent runs out of memory, its context window overflows, and it just has to give up.
So the context limit is the direct cause of failure for these complex queries.
Seems to be the primary blocker, yes.
Before we get into how ReSum fixes this, can you quickly clarify the tools these agents are actually using? It's not just one monolithic LLM doing everything, right?
Good point. It's a typical setup, really. 2 main tools. First, search. Think Google search. It takes a query, hits the web, and brings back, say, the top 10 results or snippets.
Standard stuff. And the second?
Visit. This is when the agent decides, okay, this specific web page looks promising, I need to read it. So visit takes a URL and effectively browses it.
But browsing a whole web page can return a ton of text. How does the agent pull out the specific piece of information it needs?
That's where another component comes in. They use a separate, powerful model in their case. Qwen 2.572b instructs specifically for evidence extraction after the visit action.
So the main agent decides what to do, search, visit. But when it visits, this big 72b model reads the page and pulls out the relevant quote or fact.
Exactly. This means the core reasoning agent, the one deciding the overall strategy and dealing with the memory, like their WebSailor30B, doesn't have to also be the expert extractor. It keeps things modular. The focus of this paper is purely on the memory problem.
Got it. Okay, so React builds this massive history, hits the limit. How does ReSum change the game? How does it fit into that iterative loop?
It starts the same way. The agent thinks, acts, observes, and appends that to its history, $HT. But ReSum adds a check, a compression trigger.
And what triggers the compression?
Usually it's a simple threshold. Like if the current history uses up, say, 80% of the available context window tokens.
So just before it's about to overflow.
Right. Instead of failing, the system pauses the normal loop and calls a special summary tool, which they denote chebisan.
And this summary tool reads the entire current history, $HT, all the messy back and forth.
Yes, the whole thing. And its job is to generate a compact, structured summary. They even wrap it in specific XML-like tags, summary.
What makes this summary useful? It can't just be a shorter version of the history, right?
No, it's much smarter than that. It needs to do a few key things. First, consolidate all the verified evidence found so far, like facts the agent is confident about.
Okay, distillation of knowns.
Second, and this is critical, it must explicitly list the information gaps. What does the agent still not know? What questions remain unanswered based on the goal?
Highlighting the known unknowns. That sounds really important for guiding the next steps.
It is. And third, it often suggests actionable next steps, grounded in the evidence and the gaps.
So it's not just throwing data away, it's synthesizing it into a focused state. What happens after the summary dollars is generated?
The magic happens. The huge, unwieldy history, EOT, is effectively discarded.
Wiped clean.
Well, replaced. The agent's new state becomes just the original query, plus this new summary, so let's call it summer. So some queue wears out.
So the working memory is reset to something small and manageable, but containing the distilled wisdom of the previous steps.
Exactly. And now the agent can continue its thought, action, observation loop from this compressed state colors, ready to fill more context, until it potentially needs to summarize again.
That's really clever. It keeps the simplicity of the React loop, but adds this reset mechanism, allowing theoretically infinite exploration without infinite memory.
Precisely. It maintains the key knowledge without keeping all the raw conversational turns.
Okay, let's talk about that summary tool. They built a specific model for this, ResumTool 30B. Why not just use, GPT-4 or Claude 3 Opus or some other giant off-the-shelf model to write the summary?
They tried that, or at least compared against using large models. The problem is this isn't just text summarization, it's more like goal-oriented reasoning distillation.
Meaning?
The summary tool needs to perform logical reasoning over potentially noisy and contradictory information from web searches. It has to be really good at identifying verifiable evidence versus just plausible sounding stuff.
And it needs to pinpoint those gaps and suggest relevant next steps within the web search context. A general LLM might just give generic advice.
Exactly. Generic models, especially smaller ones, often just weren't good enough at this specific complex task. They might summarize a dialogue okay, but miss the crucial reasoning elements needed for the agent to proceed effectively.
So specialization was key. How did they build ResumTool 30B?
They started with a strong base model, Qwen 3 30B A3B thinking, and fine-tuned it specifically for this summarization task.
Using what kind of data?
They collected pairs of Langle text conversation, text summary, Wrangle. The conversations were actual interaction histories from agents trying to solve challenging problems from a dataset called Sailor Fog QA problems, specifically chosen because they require long horizon reasoning. The summaries were presumably carefully crafted to be good examples of what MESM should produce.
And the results of this specialization, the paper has a table in this, right?
Yes. Table 1, it's quite striking. There's specialized 30 billion parameter ResumTool 30B, performs about as well as, or sometimes better than, much larger general purpose models when used for this specific summarization task. Yeah, we're talking models with hundreds of billions of parameters, like DeepSeek R1 671B.
Wow. So targeted training on a smaller model beat brute force scale here.
For this task, absolutely. It's a great example of how, for specific agent capabilities, smart specialization can be more effective and way more efficient than just throwing more parameters at the problem.
Okay, so we have ReSum managing the context and ResumTool creating the summaries. But the main agent itself, say WebSailor 30B, now needs to learn how to use these summaries. It starts seeing these compressed states taller instead of the full history dollars. That's a new kind of input for it.
Right, it's an out-of-distribution input compared to how it was initially trained or how standard React agents operate.
So how do you teach it to handle this? Why reinforcement learning and specifically GRPO?
Well, they could have tried supervised fine-tuning, SFT, basically showing the agent lots of examples of successful resume trajectories.
But that's expensive, right? You need expert humans or a powerful teacher model to generate all those perfect examples.
Exactly. And there's another risk with SFT. You might accidentally overwrite the agent's existing skills, its ability to use tools or reason effectively, while trying to teach it the new summary-based reasoning.
Okay, so RL avoids needing expert labels and lets the agent learn through trial and error, preserving its core skills. But why GRPO specifically? There are other RL algorithms.
GRPO stands for Generalized Policy Optimization. It's known for being quite stable and efficient, especially in complex scenarios. When you have these long sequences, broken up by summaries.
Where an action early on might only pay off much later, after a summary.
Right. You need an algorithm that can handle that delayed credit assignment and the slightly changing input distribution, because of the summaries, robustly. GRPO seems well suited for that kind of stable adaptation through self-evolution.
Makes sense. How did they structure the RL training process itself, given these summaries break up a single task into multiple phases?
They use something called trajectory segmentation. Imagine a task takes, say, 3 summaries to complete. That whole process from start to finish is one rollout. But for training, they break it down into 4 segments. In this case, dollar plus dollar segments if there are dollar summaries. Segment 1 is from the start until the first summary. Segment 2 is from the first summary state QLR until the second summary, and so on. Segment 4 is from the last summary state QLR until the final answer.
Okay, so you treat each phase between summaries as a mini episode for training purposes. But how does the reward work? The agent only knows if it got the final answer right or wrong way at the end.
That's the neat part. They avoid complex reward shaping, trying to guess if intermediate steps were good. They just use a simple trajectory level reward, $3. It's binary. 1 if the final answer is correct, checked by an LLM judge, 0 if it's wrong.
But if the reward only comes at the end, how does the agent learn that an action it took way back in segment 1 was actually crucial?
Through advantage broadcasting. First, they calculate an advantage based on that final trajectory reward, basically, how much better or worse this whole trajectory was than expected. Let's call it HE day.
Okay.
Then they take this single advantage value and they apply it, they broadcast it to every single step the agent took across all segments within that trajectory.
So even the actions in the first segment get credited or blamed based on the final outcome of the entire multi-summary process.
Exactly. It forces the agent to learn 2 things simultaneously. 1, how to reason effectively from a summary state. 2, how to act before a summary in a way that leads to a good, useful summary later on. It connects the whole chain.
Clever. It handles the credit assignment across those summary breaks. Okay, let's talk results. How did ReSum stack up against the baseline React?
Comparing the different modes is really insightful. First, just using ReSum without any RL training, using the Specialized ResumTool 30B, already gives that 4.5% average boost over React. It proves the core idea works.
And they compared it to simply truncating the history, just chopping off the oldest parts.
Yes, in simple truncation, recent history was basically useless. It often breaks the reasoning chain and performs worse than React, losing critical context. ReSum's intelligent summarization is key.
What happened when they used the Specialized ResumTool 30B with their base WebSailor 30B agent?
Performance jumped significantly. On the English benchmark, BrowseComp and WebSailor 30B using ReSum with ResumTool 30B hit 16.0% pass at 1.
And how does 16.0% compare to other, maybe even proprietary models?
It actually surpassed some well-known ones at the time of the paper, like Claude 4 Sonnet, which got 12.2%, and Kimi K2 at 14.1%. So this open source agent with ReSum was punching above its weight.
And then the RL training ResumeGRPO kicked in.
That provided the final really impressive boost. Remember that 33.3% pass at 1 on the Chinese benchmark, BrowseComp SAR? That was WebSailor 30B after being trained with ResumeGRPO.
And you mentioned the training was efficient.
Amazingly so. They achieved that 33.3% using only about 1,000 training samples. Other state-of-the-art open source agents on that benchmark, like Researcher 32B, needed 10,000 or more samples to reach much lower scores, like 15.6%.
So the GRPO training allows the agent to master the ReSum paradigm very quickly.
It seems so. It really validates their whole approach. The paradigm, the specialized tool, and the RL training method.
Now, we should address the elephant in the room, efficiency. The paper mentions ReSum takes more steps, right? Figure 5 shows it uses roughly double the tokens and tool calls compared to a React attempt. Isn't that a big drawback?
It's a fair point, and they are transparent about it. A successful ReSum run will generally be longer and use more resources than a hypothetical successful React run of the same length, or definitely more than a failed React run that terminated early.
So maybe twice the cost.
Roughly, yes. But here's the crucial context. ReSum primarily incurs this extra cost on the problems where React would have failed entirely due to context limits.
Okay, so for simple problems that React solves quickly.
ReSum also solves them quickly, often without even needing to summarize. The paper confirms this. The extra cost is paid specifically to solve the hard problems that were previously unsolvable.
So it's a trade-off. Pay 2x the cost for a chance at success on complex tasks versus paying 1x the cost for a guaranteed failure.
Exactly. When framed like that, the trade-off makes a lot of sense. It turns impossible tasks into possible ones.
And the case studies they show illustrate this, like that complex Chinese film query you mentioned earlier.
Precisely. They show a case where React would find the film title, but then likely fail when trying to find the actress's birthplace due to context limits. The ResumGRPO agent, however, finds the film, summarizes, identifying the actress, Wing An Ruki, resets, searches for her birthplace, maybe summarizes again, and then finally synthesizes the answer. It navigates multiple stages of inquiry using the summary state.
That really drives home the power of extending the agent's effective memory.
It does. The core message is pretty clear. Context length is a real bottleneck for current LLM agents, especially for web tasks, and ReSum offers a practical, effective, almost plug-and-play solution.
It modifies the existing popular React framework in a minimal way, but delivers a major capability boost in definite exploration.
Yeah, it's a significant contribution because it provides a path forward now without waiting for some hypothetical future LLM with a million-token context window that might be prohibitively expensive anyway.
So looking ahead, what's the next step for this line of research? The paper hints at something beyond the current rule-based trigger for summarization, right?
Exactly. Right now, the summary happens when the agent hits a token limit. It's a reactive, rule-based mechanism. The really exciting future direction is to make this proactive.
Meaning the agent decides for itself when to summarize.
Yes. Imagine an agent that reasons about its own reasoning process. It recognizes, okay, I've gathered a solid block of evidence on this sub-problem. Let me consolidate this into a summary state before I pivot to investigate the next angle.
That sounds like true metacognition, the agent managing its own cognitive load, its own memory.
Precisely. Moving from a system constraint, token limits, to a strategic reasoning choice. Summarize now for efficiency. That's a much deeper level of intelligence.
A fascinating challenge for future work. Well, this has been a fantastic deep dive into ResumeGRPO. Thanks for breaking down the paper with us.
My pleasure. It's definitely a technique worth watching in the agent space.
And thank you for joining us on the deep dive. We'll catch you next time.